Welcome. Until now you have learned to solve differential equations containing functions of only one independent variable, so-called ordinary differential equations. In this video we introduce a class of differential equations called partial differential equations, or PDEs, that contain two or more independent variables. And we'll take a first step in solving these equations by applying a technique called separation of variables. Many physical problems are described by partial differential equations. One example could be a PDE describing the shape of a water surface as a function of position and time. Another example could be a PDE describing the distribution of heat in a hot metal bar as a function of position and time as it cools down. Let's consider the example of the hot bar. Assume that a metal bar of length L has been heated by some source, and at a given moment you know exactly how the heat is distributed through the bar. In this graph, the initial distribution of heat is shown as a function of position in the bar, and as we let time roll, the changing heat distribution shows how the bar cools down. The question is, how can we actually calculate the change of the heat as a function of time and position? Well, let's formulate this question mathematically. First of all, note that the heat U clearly depends on position x in the bar, but at each separate position, the heat also depends on time. So, position and time are independent variables. It turns out that the rate of change of the heat at some location x in the bar is proportional to the second derivative of the heat with respect to x. That is, du dt is equal to a constant k times the second derivative of u with respect to x. Note that because u is a function of both x and t, the derivatives in the equation are partial derivatives. The resulting PDE is known as the heat equation. Now, how do we proceed to solve it? Since you already know how to solve ordinary differential equations, it would be great if we could somehow convert our PDE to a set of ODEs, maybe one for each independent variable. Well, this is exactly what the technique of separation of variables is all about. Let's illustrate the method in a couple of steps. First, assume that for the PDE there exists a solution u of x and t that we can write as the product of a position-dependent part, function capital X of position, and a time-dependent part, function capital T of time. Next, we substitute this expression for u into the PDE and work out the derivatives with respect to time and position. Note that differentiation with respect to time has no effect whatsoever on the function x, but it does convert the function t to its derivative. Similarly, differentiation with respect to position on the right-hand side only acts on capital X. The resulting derivatives are no longer partial derivatives, and they will be denoted by the primes. Okay, we are now ready to separate the variables. Divide both sides of the equation by k times x times t, and now let's take a moment to think about this equation. The left-hand side is purely a function of time, whereas the right-hand side is purely a function of position. What happens if we change the value of time on the left-hand side? Well, clearly the right-hand side is not a function of time and must stay constant. And because the right-hand side equals the left-hand side stays constant as well. Similarly, if we change the value of x on the right-hand side, both sides of the equations must stay constant. Let's call this constant lambda. Finally, the left and the right-hand side, they give us a pair of ODEs which can be rewritten in this form. Now that we have converted our PDE into a set of ODEs, let's have a quick look at some solutions. Note that for different values of lambda, we will find different solutions for capital X and capital T. For example, when lambda equals minus the square of pi over L, we find the following solution. The spatial distribution of the heat at each instant of time is a sine function, but as time progresses, the amplitude of the sign will decay exponentially. Okay. Another solution is obtained when lambda equals minus the square of 3 pi over L. Note that in this case the exponential decay of the heat profile happens much faster. Good. That's it for now. You have learned the technique of separation of variables. Keep in mind that this is only a first step in solving PDEs. The solutions shown in this video are examples of so-called fundamental solutions. They are obtained by applying the heat equation with a specific set of boundary conditions, and they are the building blocks for more general solutions. You will learn more about this in the next couple of lectures. See you there.